Hello everyone, myself Vatsal Mehta from Team Tensor Titan. My team has engineered the UrbanEye. If I have to describe my project in a few words, it is a smart and intelligent geospatial tool using which one can identify what has changed in Earth for a given time period. The gist of my project includes it uses three different sources to fetch satellite images. It leverages transformer based architecture to detect pixel precise urban modification. It computes six different scientific indices to validate the score from the change detection model. It is capable of generating smart and intelligent reports using integrated large language models. And all those tasks which I previously mentioned are quite monotonous and requires manual setup. To deal with it, my team has engineered an autonomous agent called ORION. It translates the conversational prompts into complex and automated workflows. Let me demonstrate it. Fetching desired satellite images involves crisp, simple steps. First, you select area of your interest. Next, you select the date for time period T1. And later, you select the date for time period T2. For example, let us consider an area South Bhopal, an area from Ahmedabad which we know has gone through a significant amount of changes. So we will randomly select an area of interest from South Bhopal and we will try to find out what has changed for our selected area of interest between the year 2018 and the year 2026. The year 2026. These color-coded dates which you see on your screen right now are actually the valid dates when the satellite has actually visited the area of interest which we selected. We will be notified once the pipeline finished fetching the satellite images. So in the meantime, let's go over to the technical aspects of my project. If you were a non-technical viewer, feel free to skip this section. As I mentioned earlier, my project uses three different sources to fetch satellite images. The first is the Google Earth Engine. It is quite visible that the image from Google Earth Engine is pixelated and it does not perform well in the inference. For example, I have selected an area of interest and I have used Google Earth Engine for fetching the satellite images. And this were the image which I was able to fetch. And this is how it works for inference. You get a complete black spot. Okay. Next, we have a better source called Planet Lab. It improves the performance of it improves the quality of performance, but we can see the image is still blur. And finally, we have S2DR3, a super resolution image with 1 meter of accuracy. This provides best and most clear fine details. It works best with our deep learning model, as observed by our team. The change detection model. The project uses pre-trained transformer-based architecture called ChangeFormer, for which I would like to take a moment and thank the foundational work by Vishal Patel and his mate. This is the GitHub repository followed by a detailed README file. If I have to describe this architecture briefly, the model takes two images, before and after, passes them through same CMS encoder. This encoder shares weights and performs similar feature extraction for both the images, ensuring consistent pixel precise comparison. Later, the decoder is responsible for unsampling the information and converting it into a binary change mask. Here, 0 indicates no change and 1 indicates change. Later, I have fine-tuned this model using OSCD dataset. OSCD stands for Onera Satellite Change Detection Dataset, which is freely available in this IEEE data port channel or website. What you see on your screen right now are some exciting features about my project, but I would rather show them in action than just talk about it. Okay, so the image you see on your left is the baseline image, a random area from South Bhopal from the year 2018. And what you see on your right is the same image, but from the year 2026 from South Bhopal. Now let's see change detection model in action. As it is clearly visible that some area of this image has undergone some minor changes, and this particular region has undergone significant amount of changes. This is the binary change mask where 1 represents that the change was detected. This white pixel denotes that the change was detected and 0 indicates that there was no change. You also get a too long didn't read description of how the project came up with this solution. Okay, so deep learning model and AI are very smart and powerful, but they still make some mistakes. To make our predictions more reliable, we use scientific spectral indices. These indices are calculated using mathematical formulas. The color spectrum helps us interpret the result with the values which varies from -1 to 1. This index is for vegetation. This is for built up index. This is the water index, bare soil index, and hence vegetable index. Urban planners can easily create and manage rules based on local regulations. These rules are automatically applied to the intelligent layer, making the output both intelligent and compliant. For example, I have created a rule which says no new construction near Vastrapur. Construction near Vastrapur was not allowed as it is highly dense area. Okay, so we are not just building tools. We are building an intelligent system that does the work for you. So far, everything we have seen still requires some level of manual setup. And to solve that, my team has built ORION, our autonomous geospatial agent. With the ORION, you simply describe what you want in plain language, and the agent converts it into a workflow. For example, analyzing data, generating insights, all automated. This proud feature was designed and developed by my teammate Vedant Kalal. I would like to thank Tirth for designing endpoints and ensuring everything is well integrated. This is Vatsal Mehta signing off.